Welcome to Paint the Past. I'm your host, Amaris. What I'm painting today is a fossil ammonite, specifically one of the Dichotomosphinctes genus from the Oxfordian stage of the late Jurassic. All that sounds very technical, but what it means is that this is the remains of a creature that was alive and swimming around in a shallow sea approximately 160 million years ago. When this animal was alive, there were sauropod dinosaurs walking on the land above those seas. It was a time when Stegosaurus was around and pterosaurs were in the air. The world looked almost nothing like it does today. And this coiled shell sat in the sediment through all of it. Through the age of dinosaurs, through the mass extinction that ended that age, through the entire history of mammals, through every human civilization that has ever existed, every war, every plague, every invention, every piece of music ever composed. It just sat there. And I'm going to paint it. The reference photo I'm using today is by Jane St. John via Wikimedia Commons, and I'll provide a link in the description below the video. I want to spend some time today talking about what this creature actually was, what the world was like when it was alive, how it worked as an animal, and some of the genuinely strange things paleontologists have figured out about ammonites in general. Because there's more going on here than a pretty spiral. But first, let's take a look at what our ancestors thought about these ancient animals. The name ammonite comes from the ancient Romans. Pliny the Elder, the Roman naturalist who died watching the eruption of Vesuvius in 79 CE with notebook in hand, which tells you something about some kinds of scientists, Pliny called ammonite fossils Ammonis cornua, the horns of Ammon. Ammon being the Egyptian god often depicted wearing ram's horns. And the spiral coil of an ammonite shell does look a bit like a ram's horn from the right angle. In England, ammonite fossils were called snake stones well into the early modern period because people thought they looked like coiled snakes that had been turned to stone. In the town of Whitby on the Yorkshire coast, which is rich in Jurassic ammonite fossils, people used to sell ammonites with a carved snake's head added to the end to support the legend. You can still buy ammonites in Whitby today, though thankfully they tend not to add the carved heads anymore. According to medieval legend, St. Hild, the abbess of Whitby, had turned a plague of serpents into stone by praying at them. The fossils were the proof. Meanwhile, in India, ammonites are called shaligrams, and they've been considered sacred objects for millennia, associated with the god Vishnu. A fossil that a Jurassic paleontologist classifies as a cephalopod mollusk, a medieval English person classified as a petrified snake, and an ancient Hindu tradition classified as a divine object. They're all the same spiral-shelled animal. The object stays the same, only the human interpretation changes. But let's move on to how they're understood by modern science. Dichotomosphinctes belongs to the family Perisphinctidae, a large and diverse group of ammonites that were dominant in the Jurassic seas. They were particularly common in the late Jurassic, roughly 163 to 157 million years ago, and fossils of the genus have been found across Europe, including England and France, as well as India, Argentina, and Madagascar, where this one came from. That global distribution tells us something important. These creatures were living in a world where the oceans were connected in ways that they aren't today. And these creatures were good at spreading across those connected seas. To understand what this animal's life was like, you have to abandon almost everything you know about the geography of the modern world. In this part of the Jurassic, Pangaea, the supercontinent that had included most of the world's landmass, was in the process of breaking up, but it hadn't finished yet. The Atlantic Ocean was young and much narrower than it is today. What is now Europe was an archipelago of tropical islands and shallow seas. Much of what is now England, France, Germany, and Poland was underwater, a warm, shallow sea connected to the vast Tethys Ocean, which wrapped almost all the way around the equator. And warm is the key word. The Earth in the Jurassic was, for the most part, a greenhouse world. There were no polar ice caps, or at most only very minor glaciation. The poles were cool and forested rather than frozen. Sea levels were rising through the Jurassic, peaking perhaps 100 meters or more above present-day levels at certain points, which is why so much of Europe was underwater. Global temperatures were significantly higher than today. The atmosphere also had more carbon dioxide, the result of extensive volcanic and seafloor spreading activity associated with the ongoing breakup of Pangaea. That CO2 acted as a greenhouse gas, keeping air temperatures elevated and ocean temperatures warm. Ocean circulation was sluggish because there were fewer temperature and density differences between equatorial and polar waters. And on the land adjacent to those seas, the famous Jurassic fauna was in full swing. The late Jurassic, around the time our ammonite was alive, is the period of Brachiosaurus, Diplodocus, Allosaurus, and Stegosaurus. Archaeopteryx, the earliest known bird, appeared in what's now Bavaria, Germany. Our ammonite was not alone in those warm seas. And it wasn't at the top of the food chain either. Not by a long shot. The Jurassic oceans were dominated by marine reptiles that had evolved from land-dwelling ancestors millions of years earlier, which is remarkable in itself since those ancestors had no connection to the sea. By the late Jurassic, you had two main groups ruling the water. The ichthyosaurs were the fish-shaped ones, streamlined, fast, and dolphin-like, with large eyes adapted for hunting in deep or murky water. The word ichthyosaur means fish lizard, which is a bit of a misnomer. They weren't fish, and they weren't technically lizards either, but they had independently evolved the fish body shape through convergent evolution, the same process that would later produce dolphins, which, as I'm sure you've noticed, are fish-shaped mammals. Then there were the plesiosaurs, that are far more alien in their body plan. They came in two main varieties. The plesiosaurids had small heads and very long necks, shaped vaguely like a snake threaded through a barrel that has fins on it. Pretty weird. The pliosaurs had enormous heads and short necks. The largest pliosaurs of the Jurassic were among the biggest apex predators in the entire history of the oceans, reaching perhaps 10 to 12 meters in length, with jaws that could probably take a large chunk out of almost anything they encountered. Large, modern-style sharks were also present by this point. Marine crocodilians, actual relatives of modern crocodiles, patrolled shallower coastal waters. And the seas were thick with fish, squid-like belemnites, and, of course, enormous numbers of ammonites. Geologists estimate that ammonites were so abundant in the Jurassic oceans that they were genuinely one of the dominant forms of marine animal life. They were diverse, numerous, and widespread. For our Dichotomosphinctes ammonite, this meant navigating a world with a lot of things that could eat it. Here's the thing about ammonites that doesn't get said often enough. They were not just the shells. The shell is what we find now. The animal is what we almost never find because it was soft, and soft things don't fossilize well. What lived inside that beautiful spiral was a cephalopod mollusk, not related to snails, but rather to squid, octopuses, and cuttlefish. People tend to picture ammonites as something like a nautilus, because the nautilus is the only currently living shelled cephalopod, and the shells do look similar. But research suggests ammonites were actually more closely related to the coleoids, the squid and octopus group, which means the body inside the shell was probably more squid-like than nautilus-like. The best current guess is that ammonites had around 10 arms, rather than the dozens of tentacles that a nautilus has. The shell itself is a masterpiece of engineering. It was divided internally into chambers. The animal only lived in the outermost, largest chamber, the body chamber. The older, smaller chambers were sealed off as the animal grew, and the animal could pump gas or liquid into them, through a thin tube called the siphuncle to adjust its buoyancy like a submarine ballast system. This ability is why ammonites could be found at various depths in the water column, rather than just sinking to the bottom. In 2021, a team from Cardiff University and Imperial College London published a landmark study in the journal Geology. They had used high-resolution X-ray and neutron imaging to create a three-dimensional reconstruction of an exceptionally preserved Jurassic Ammonite from Gloucestershire. The first time anyone had visualized the soft tissues of an ammonite in 3D. They found the hyponome, a tube-like structure that ammonites used for jet propulsion, squirting water to move, exactly like a modern squid does. They also found powerful retractor muscles the animal could use to pull itself back into the shell. What they didn't find was an ink sac, so it looks like at least some varieties of ammonites lacked the ink-squirting tendencies of their squid cousins, which perhaps explains why they developed such solid shells. One of the most remarkable things that paleontologists have worked out about ammonites in general, and about the perisphinctid group that includes our dichotomosphinctes in particular, is that they were very strongly sexually dimorphic, meaning males and females looked very different. The convention is that ammonite species came in two forms. The macroconch is the large form, with a simple, plain aperture, the opening of the shell. The microconch is the smaller form, with distinctive wing-like projections called lappets extending from the aperture. For a long time, these were classified as completely different species, because they looked so different. Scientists later worked out that they were actually the same species, just the males and the females. The current consensus is that the macroconch is female, and the microconch is male. The females grew much larger, an adaptation thought to be related to producing and carrying eggs. The males' lappets may have been involved in reproduction, though their precise function is still debated. In some Jurassic perisphinctid species, the size difference between male and female is extraordinary. The macroconch can be many times the diameter of the microconch. And for over a century, researchers were cataloging what were actually two sexes of the same species as entirely different animals, with different genus names. Ammonites are arguably the most useful fossils in the geological record, not because of anything dramatic about their biology, but because of a combination of properties that make them extraordinary tools for telling time. Think about what you need in a good geological clock. You need an organism that was widespread, found all over the world, not just in one region. You need one that evolved rapidly, so that each species was distinct and existed only for a short span of time before it changed into something else. You need one whose remains were hard enough to fossilize reliably, and you need one that is distinctive enough that you can identify the species just by looking at the fossil. Ammonites tick all of those boxes. Each ammonite species typically only existed for a few 100,000 years before it evolved into something different or went extinct. By the standards of geology, that's almost no time at all. Which means, if you find a particular ammonite species in a rock layer, you can often date that layer very precisely. Geologists can divide up parts of the Jurassic and Cretaceous periods into sections of only a few 100,000 years, based on ammonite fossils. No other group of fossils gives you that kind of precision across that time span. The practical importance of this also extends well beyond the academic. The Jurassic rocks of the North Sea, for instance, are a major oil reserve, and every time geologists and petroleum engineers drill into the seafloor and pull up a core, ammonites are among the fossils they look for to determine exactly which layer of rock they've hit. The little spiral creatures that lived in those Jurassic seas are still doing work 160 million years later. The ammonites seem to survive everything. They survived the late Devonian mass extinction, They survived the end Permian extinction, which was the biggest mass extinction in the history of complex life, and wiped out over 90% of marine species. After that catastrophe, only a handful of ammonite types remained. But from those survivors, they radiated explosively into hundreds of new forms in the early Jurassic. They survived the end Triassic extinction too, which killed off about a third of all marine families. They seemed untouchable. And then, 66 million years ago, the asteroid hit. The Chicxulub impactor, a rock perhaps 10 to 15 kilometers across, struck what is now the Gulf of Mexico with the force of billions of nuclear bombs. It triggered earthquakes, tsunamis, wildfires, and most devastatingly, blasted so much rock dust and soot into the upper atmosphere that it blocked sunlight for years, collapsing food chains from the bottom up. Because of the lack of sunlight, photosynthesis was drastically reduced. Marine plankton, the base of the ocean food web, collapsed, and ammonites, which appeared to have laid eggs that floated with plankton at the sea surface, were catastrophically exposed to the disruption near the water's surface. The nautiluses, their more distant relatives, survived, perhaps because they laid fewer, larger, tougher eggs on the seafloor, insulated from the worst effects. The ammonites didn't make it. After a run of over 300 million years, every single species died at or very shortly after the asteroid impact, and the world has been without them ever since. Which makes this fossil, in a way, the record of a remarkable evolutionary lineage at its zenith. Dichotomosphinctes lived roughly 95 million years before the asteroid, so when this particular animal died and sank to the seafloor, there was no indication that the story of ammonites would be ending anytime soon. Thank you for joining me for a swim in the late Jurassic seas. I hope you enjoyed the episode and will consider tuning in to future ones. If you have ideas for paintable artifacts with interesting stories, I'd love to hear about them in the comments. See you next time!